my side. My name is Thomas Becker. I'm a food and bioprocess engineer by education, and with a focus mostly on engineering and digitalization aspects. Yes, and before I go to the next slides, I will really focus on 3 pillars, which are the motivation for this project. The first one is, with our project, we want to really go a new way for food provision, food production, food processing, basically based upon palm profiles. What palm profiles are, I will explain later on. The second pillar we want to consider is we want to be with our raw materials using and the processing as much as possible independent of landscape and climate change. And the third is, it's as important, we want to work with a primary agricultural products. Everybody knows that when we are talking about meat, conventional meat, we use 4 to 6 kilogram proteins for having at the end 1 kilogram of animal proteins. So these are the 3 main pillars we want to address with our project Proteins4Singapore. Now, during this conference, all is said about climate change, but not from everybody. I will also stress it out and repeat a bit what is mostly concerned with food provision, food production, and food consumption. The first is we have really a global change in urbanization. When we are looking how many citizens are living in an urban residence, it's at the moment almost 50 to 60% worldwide. And it's expected to 2050 that almost 70% of the urban residents are occupied by the people. And what is also important in this concern, that urban areas occupy only less than 1% of the Earth's land area. And this is really a strong challenge to the food provision to the consumer, because we must bring the food into these urban centers with all upcoming changes in the food supply chain and what all is concerned and related to this. The next point, which is very important, is that most of the energy we consume is utilized by the cities. This has also a strong effect to pollution. And when we are looking where the food are supplied and consumed, this is almost also 80% of all food supplied. This is very, very important to consider. The third aspect is the climate change itself. Yes, we know that we must feed at the end of this century 10 billion people. We will become more people worldwide. And the food production, if everybody is using the foods in the same way as today, with the same habits, we need an increase of 70%. But if somebody is changing his consuming habits, perhaps he wants to eat more meat, this number is not really true for a forecast. And what is also very important, when we are looking at the landscape usage, with a 1 degree Celsius increase of temperature overall, we lose a yield of about 10% of agricultural productivity. And this is really very important when we are looking at food provision, food production, and production of raw materials for them. And the next point, and this is also very, very important, I think we have a strong food waste at the moment worldwide. 1/3, 30 to 40% of the worldwide food production is wasted somewhere, at the agricultural landscape, at the households, or in the processing industry. And this is also somehow a source we can perhaps reactivate and revalorize to new food products. And what is also very important we have to consider is that 2 billion citizens will be overweighted and 3 billion underweighted till 2050. And this is also to consider when we are talking of foods for the next decades. And this is also what I already said, that very, very many people want to change their habits, what kind of foods they're eating. They want to have high valorized and meat-based fats. And this is also very challenging and interesting for landscape usage and production of agricultural raw material. And it's really when we are talking about this is now our strategy. We want to really produce new technologies to produce traditional. Yes, this is very important because the consumer is expecting somehow a shape of his foods or new foods with sustainable resources in. hopefully as much as possible in a no-waste agenda. And let's address the most important future trend for food innovations. I think in the center of all innovations activity, more and more the consumer is focused. We must look consumer-centered. What does the consumer prefer? What does he accept, and what does he need? And these are the palm profiles. And think all what we are doing in the future, the consumer is sitting in the middle of all. And when we are looking at these three areas, I see the areas where most of the innovations are done. This is the first, on the left-hand side, the palm-driven valorization. The second is we must bring more digitalization aspects into the food provision, food processing, food production, and the relation between foods and the habits of the consumer, of the society. And we need really intelligent technologies to really overcome all the problems we have, and we can really forecast for the next time. But what is very, very interesting, we have here a triangle between economy, ecology, and society. And this triangle, the corner of these triangles are not independent to each other. I think if we pull at the one corner, let's say at the economy aspects, the other ones, the ecology and society, is very much concerned with this. And this balance must fit totally to the society, to the personal interest, to the market, and to whatever. And here you see in these lila color, the things we are addressing with our Proteins for Singapore approach. I think we want to really go new ways for structuring foods, for texture design, soft matter aspects. We want to really look how much we can replace conventional raw material by new ones or totally another ones. We want to go really a reverse engineering approach, what I will explain later on. And we want to use, indeed, this is my personal interest, especially I worked since 30 years about this. It was with digitalization aspects, net-based cyber-physical process and production schemes, very important. And these are the main working places we are interested in. We are working in our Proteins for Singapore project. So what is reverse engineering in respect to food systems? I think this is not an invention by myself or by us as a group. I think it's a very, very well-known and established way of working in other industrial areas like the automotive industry, space engineering, medical applications, sports, whatever. Yeah. And what is the principal idea of this reverse engineering approach? I think we are looking mainly at the end product. How does the end product look like? And really going back from this perspective, how can we reach these properties, this shape or whatever? Hey, in automotive industry, we want to have really, let's say, the scratches or 3D models of the principal basic units. In food engineering, we see it a bit different. We want, and we must use product knowledge and must have really a knowledge about structural information of the end product. And with this, let's say, properties we want to have at the end, we must build up relation to raw material behavior, process behavior, or analytical measuring systems. And this is really a new perspective how to really produce foods. And this needs really basic research at the moment and a strong development. But as well, we need also the translational aspects to consider from the scratch. I think we have to really look, how can we really move this into the market, to the consumer, and this should be considered from the very beginning of these research proposals. Let's go a bit more inside how these engineering approach and palm profiles are working and how we are seeing this and how it's defined. We can work, and this is done since decades, traditionally recite or recipe raw material based, more or less like a cook. We have more raw materials traditional, we know all of them, and we process them in different processing steps. We have intermediate substances, substrates, products, and we have flow material from the raw material to the end product. This is quite what we are doing since decades, since centuries, yeah, like a cook. And at the end, what is important is really to have end products. And these end products, we will bring totally into the consideration of our future work. We must have really more and more at the moment at the consumers, pleasuring, safe, stable, typically convenient and healthy products. but not products, but properties of the products. And this is what I see and is considered very intensively more and more. These are the pawn profiles we are looking at: preferences, acceptance, and need of the consumer. And now we want to change really, and when we want to analyze this is already done also since years. Yes. We must look at the different scales to really analyze, measure, elucidate the properties. We can look at the macro scale, yes, at the shape of the food product. We are looking at the micro scale, structures, nanoscale, and molecular. And in each of these intermediate unit operation steps, we can really consider these different levels of scalability. And this is what is already done. But we want to go really another way. We want to go to a reverse engineering approach. We are more or less sticky to the end product properties. And we are asking ourselves, how can we reach these properties? Is it necessary to really follow all these typical processing steps? Is it really mandatory to use the raw materials conventionally? Or can we really make a change in thinking and say, okay, the end product property must fit, and we must look how we can reach this with unconventional raw material, with unconventional processing, which are normally used in food processing. Let's make really a very easy food product in a traditional food production process. It's bread. We are working very intensively with cereal-based foods, and bread is one of the most important ones. And we have typically the raw materials: flour, yeast, salt, sugar, and tip water. We have a production process. We must hydrate them, bring water inside. We have to mix and knead it. We have some resting step to have the reaction rates necessary. And you have molding, proofing. At the end, we have a temperature procedure with the baking. And at the end, we have final products. You know them. We all know them. A solid, open cell foam structure. And this is important. Structure, we are talking about structure. And we have, as well, when we have it at the end and continuous rehydration and forming of the stuff. And the consumer accepted must look at the shelf life and has to oral process it or consume it. And now let's look at this easy example. We are looking at the end product. It is important to have at the consumer a sensorical impression which fits to the expectation. It must be fluffy, it must be elastic, must be crispy somehow, depending on the expectation. And the sensorical, let's say, shape must fit exactly to what the consumer will have. But do we stick? It is necessary to stick to the raw materials, and this is exactly what we wanna do here. And hey, is it possible perhaps to make bread out of wood, out of lignocellulose? This is what we already did, and it looks like a bread when we did it with wood or a lignocellulose-based raw material. It was very crumpy. It was a foam what we could produce. It was very the shape was also a crust, but it was hard as a stone. So I think this is a first impression. Hey, how to produce quality is not sufficient enough, but it's a first primary step. And here we can really go new ways, and perhaps at the end we can really bread, yes, comparable product with typically other raw materials. And hey, let us go one step deeper. And this is what you already did at wheat dough. Wheat dough, you know, it's a primary intermediate material for having the bread. And in order to develop an artificial dough system, we can see the dough as a three-component system. Yeah. And it's really so we have the gluten network. Yeah. And can it be replaced by a mixture of natural or synthetic polymers? That is what we were asking ourselves. Yeah, offering the advantage of standardization is one thing, and replacing the raw material wheat with other materials which fits in the properties nearly the same as we expect from the gluten proteins. And why using starch granulars? Why not using glass beads? Yeah. And glass beads is the same size, and we have two different distributions or different, let's say, medians when we are looking at the sizes, diameters of the starch granulars. Why not replacing by glass beads? Yeah, this is not working very properly at the moment. We have to functionalize the surface of these glass beads, And then we could really build up an artificial dough without any wheat, without any gluten network, and without any starch granules. And when we are looking at the corresponding mechanical properties here, we are seeing it in the higher part of the slides already some research from this dough example, and we fit with our synthetic reconstituted raw material in processing very good to the values done over this power law fit of G dash to wheat dough. Look at the way of N and K. This is very usual when we are talking about elasticity or firmness. It's very good. And this is in the let's say in the small scale deformation, but as well in the large scale deformation, when we blow up more or less here, blow up the dough or the material of the batter, we have also a typical behavior with an rear fermentometer done with the original wheat dough. So we can really see what, and here in the left, in the right hand side, you see the intermediate material. We are looking at different scales. You can imagine with SEM, with a confocal laser microscope, whatever, to really see what is the functional behavior, what is the relation between the different components to get at the end such a matter which can be blown up like it's done in a bread production process conventionally. So, and this is really the point where we want to tackle in our Proteins for Singapore project. We must look to protein sources which have functionalities fitting to build up different structures. And this is very interesting. And we are sticky to plants or to, let's say, microalgae. And we can think about now by taking soybeans. This is what I will address later on. But here, I think we have the opportunity or the possibility to use different plant sources, extract proteins functionalities with extraction processes and whatever, and bring them in a new innovative production scheme to have at the end a product which fits in the parameter, crispiness, whatever, softness, flavoring, pleasure, whatever, to the product the consumer is expecting. We have to do this very carefully, but because we may not only look at the functionalities, we must also look to the tolerability, to the availability, how much does this cost. Also, we must look to the production cost. Consumer acceptance is especially in Europe, it's a dramatic point there. When you do not have a consumer acceptance, or when you produce a food not conventionally done, what is since let's say some 100 years, I think you will not easily get an acceptance by the consumer, and it must be somehow also sustainable with landscape uses and climate aspects. Yeah, but this is very important, and we will stick in our project especially to those plant protein sources. Yeah, and we are looking at microalgae. Not too much at insects. This is not dealt with in this project. This is what you're doing, or I personally do in other things. But here we want to stick at the plant protein sources. And here give also a very interesting example where we can replace the one or the other raw material by another one. It's a vital gluten is upcycling waste product of the starch production. And what we wanted to do here is to replace the typical meal, the typical wheat meal by such a vital gluten stuff. And here you see as well that we have really good success. It's really a real product, what we see here in the middle of this chain. It's a real product. And we can really replace by a very huge ratio the typical wheat flour by such a vital gluten. And here, what is also very important, what is shown in the right hand side here of this slice. We must work not as a descriptor. We must really understand which functionalities can be measured with which analytical system, and how can this relate it or model to the end product quality. And here we are very intensively working with our biophysicists together to really find out which structure regimes of the different proteins fits to which functionality in processing and at the end in the end product. And this is already done here at the publication very shortly, publicated by Beverly et al. Is a PhD student of mine, where we can really build up this modeling from end product quality, process behavior, and functionalities of proteins. And here, this was the motivation to build up these Proteins for Singapore project. And now the question is, doing it alone is nice, sometimes sufficient, but I think you must build up synergism. You must looking for complementarities. And here, I think we have a very strong consortium built up with the NTU University, as far as I know. They are very strong in basic material science and digitalization approaches, yeah. And we do not need, as a TUM here in Germany or in Weinsteffer, we do not need a university who knows the same than me or than us, who are very reputed in food science and food engineering. This is what we can do for us alone. We need somebody who is complementary to our skills, and I think the university partner of NTU is very, very, very good fitting to this consideration. And what is also important, we want to have some, let's say, local players, key players at Singapore to be incorporated. And I think with the Singaporean Institute Food and Biotechnology Innovation and the Singapore Institute of Technology, we have really some very strong local partner which know the landscape in Singapore and can bring these translation, especially in translational aspects, to our more basic fundamental science we are doing at the universities. And at the moment, we are supported by from these three units, we have a strong commitment to co-finance or contribute to our activity with Nestlé, Symrise, and EIT Food. EIT Food is a consortium inside Europe, and 1.4 billion project there. We are involved as TUM, and these are a constellation in our thinking where we can really make basic science at the one side and bring really translational industrial aspects very soon into the workflow of this project. This was the reason why we were building up this constellation. And the next is the structuring of these Proteins for Singapore project. I think we have 3 or 4 or 5 main topics. The one is the raw material topic. So at the one side, we must have new protein sources or producing protein equipment without using landscape. What we must free, in which protein sources we are sticking to. I think soybeans are very well established at the moment in an agricultural cultivation process. A lot of is known, but soybeans, are very good in their protein functionalities. They are comparable to the animal ones and to other ones as well. And what is important for the workflow of the whole project, with soybeans, we can primarily using really conventional soybeans, they mill them, extract them, then you can directly go into topic 2 or 3, really using building up knowledge which functionalities of proteins are useful for the one or the other texture or structure profile. This is very important why we are saying go into soybeans. And the next point is soybeans is very erosive to landscape. It's very intensive in cultivation. And algae is a very important point or a very, very interesting and favorable protein production for the future. And this is very important. If we are looking at those protein functionalities, we are not using directly the original raw material. We want to extract protein, let's say cocktails, with extraction or a hydrolysate processing to be able to have at the end raw materials for the topic 3 for the various food engineering process. And what is very important is here this characterization platform. In topic 4, we summarized all analytical and measuring stuff together in one topic. Yeah, they are normally used for analyzing all intermediate products in topic 1, 2, or 3. And they have also to do some, let's say, nutritional science work or food safety work to be at the end able to say, okay, what we are producing is safe somehow and can be really provided to the consumer. This is the overall structure. And I will now go a bit more in this reverse engineering or reverse food engineering approach. And here you see here the already realized 3D food printing system, and you see here a self-produced 3D printer, and it's not a conventional one. I think when you're looking at 3D printing and 3D printing stuff, also the NTU has a long experiences. you're using normally homogeneous paste or matter, and you put it in a pistol and you press something out, and then you have the shapes what you here see at the tomb and the tomb icon. But this is not the thing we are interested in. This is already done already, and in the market with food or food stuff or whatever we can say to this. It's really a shaping of the geometries, how a food or a material or a plant or whatever is looking like. But you build up not structure so far with these 3D printing systems already known. And this is what we want to do here in our approach. We want to build up really structures within a 3D printing system. And for us, it's important to see, or it's normally how we will see this. We say, okay, we have a constellation with an extruder system, not only a simple or a lone extruder, also in co-extrusion systems or extrusions in parallel, and a 3D manipulator. And what we expect as well is to have a post-processing unit. We stick here, what we will see in the next slide, to a radiation unit. Here you see already a 3D printing system for building up food structures with an own constructed system. And you see here what's going over the unit, over the body, is an infrared beam where we stabilize somehow the structure. And this is what he already did. What you see here, we combined this with an imaging system not to know the overall shape of the system, but it's important when you are doing it in the way we are doing, that you have after the outlet of the nozzle, not, let's say, a post-transformation of the material. It may not flow too much and really destroy the structure you did in before. I think it's very important to have really an imaging system to see, okay, what is the post-flow or the post-movement of the materials? And then we can really change in an adaptive system the pressure or the temperature or the move on of the 3D manipulator. And this is what you already did with, let's say, a serial-based raw materials. And what is important as well when you're doing or going this way is really building up structures and texture, bring also very new insights and possibilities with flavoring aspects. We did it already in a very intensive project and a big project with natrium chloride salt localization and perception with Corina David, a co-PI of this project, where we really build up layer where salt is inside and salt is not inside. And we got the result, and this is well known, because our sensory impression is more sensitive to gradients in substances than to an overall average concentration. And we could really reduce the overall salt amount inside this unit only by building up heterogeneous structured points of salt. And this is very interesting. We are using here the same as before. As I said, we have here two extruder systems in parallel and have NER heating with a 3D manipulator. I'm looking at the time. I do not know how much I will have. Still, I have only some more slides. And here it's also very interesting what we are doing. We must understand the material properties, and we combine this with an FEM modeling. What you see here is a structure from 6 millimeters, and we want to really understand which structure, which a configuration, body centered cubic or a simple cubic or a face centered cubic configuration, because we are totally free in the type of configuration of grids, what we are doing with our 3D printer. And we combine this with the modeling approach to really see the mechanical properties when we are going from a scale micro, mini to macro. And this is what we all want to do in this project, to really bring this to a modeling aspect, to have a broader application or a higher visibility of the overall behavior of the whole unit. So let's go to the last 3 slides. Is this really the end of 3D printing for foods? I think we must go a step ahead, not only to really principally reanalyze or redesign a 3D printer, what we already are doing, but to come to a platform which can be used principally for for a huge area of foods. And here we are thinking we should really combine these protein structure and texture manipulation with a more conventional multi-extruder system, 3D manipulator, and a 3 post-processing unit in a scale, let's say, not having gram per hour as an output, but having kilograms per hour output, in more or less in an industrial technical setup. And this is really the principal idea, to have really multi-extruder system with different nozzle system and a 3D manipulator, what is in principle a 3D printer. And we see it as necessary at the moment to really have a post-processing unit. This is what we are realizing mainly, as it seems now, with a radiation system. And this at the end should be a platform system where we are free in producing different structures, fibrillar structures, globular structure, or foamy structures, what you already realized in the foamy stuff. And this should be really a platform technology, and with a reverse food engineering approach based upon the end product properties, and looking how we can reach this when we really have a knowledge and a model of the end product relation to the raw material or the intermediate behavior or measuring system. So what is really important for us is here that we do not work as a cook. We do not want to work as a descriptor. We want to really build up fundamental material science knowledge, which functionalities relates to which structure and texture, behavior, or shape. And we want to be as much as possible free of the raw material. We only want to have an intermediate description or a formulation of the properties of the protein cocktail to get at the end the one or the other shape. We have to have a really mechanistic understanding of all what we are doing, and we want to have really produce realistic texture. We are not sticking to foamy structures, what we already did in our lab. We want to extend it to fibrillar systems in this co-extrusion system we already presented, or our globular disperse systems. We want to build really up a globular and platform technology with our combination extruder, 3D manipulator, and post-processing unit to build up to be able to build up really different foods with different shapes, textures, structures, whatever. And this is important, and this is the base of our whole Proteins for Singapore approach. Hopefully, I could bring you this project a bit closer, and I would be happy if I would have some questions to answer. Thank you very much.
Thank you very much, Prof. Becker.
I do not know at the moment how much time I needed.
You've actually slightly exceeded, so now it's the time for Q&A. So if anyone has any questions, please either raise your hand or type your question into the Q&A box, please. Dr. Lim, please.
I guess while people are still constructing the question, Professor Becker, I'm intrigued by your comment that the example that the gradient of salt that you can engineer into food affects the perception of saltiness. So do you see a role for the neurosciences into this research? So,
yeah. Very, very interesting question when I can directly answer to this. This is indeed the point. Our sensorical equipment, our receptors are working, like I said, they are more sensitive to gradients. Yes, so if you have gradients in salt, you accept this more. And this is interesting, but it's mainly done in our brain. What we did in another project, already not here inside this Proteins for Singapore, we also stimulated some nerves in a beverage project, some nerves to really change the perception or the acceptance of non-alcoholic beer. So we did some ingredients inside which changed a bit, let's say, the brain constitution, and then you have another acceptance or, let's say, perception of this type of beverage. I think this linkage from real sensorical stuff to brain working or brain behavior is a very interesting one, which will come up the next years very intensively, I'm sure about this. But this we will not address in this Proteins for Singapore project, perhaps in an upcoming or a next one. But I think this is not addressed here. But I personally work exactly at this field to manipulate somehow the thinking in your brain about the food you are eating.
Okay. And while we're waiting for others who might, I think there's a follow-up question from an attendee, Michelle.
Yes. So there's a question from Hong Yuan. Hong Yuan, would you like to ask a question now?
Please do. Nobody has a question. This can be a good or a bad sign. Depends.
I think he's unmuted himself now. Yeah.
Okay, can you hear me now?
Yes.
Okay, thank you very much. I think I need to unmute, but I cannot find the place to unmute. So, Prof. Thomas, well, so because you have a long talk and I have one educational question. So you talk about some concept of the reverse engineering, right? So maybe I don't do the food. So at a very high level, can you briefly describe what exactly is reverse engineering?
Yeah, reverse engineering is not an invention by ourselves. It's already done since a couple of years in other industrial areas. I said it. You look mainly at the end product shape or property. Yeah, you are only interested how crispiness or how soft, how how is the sensorical equipment is of your product, and you are not sticking to a conventional raw material and to conventional processing step. You look from a totally different perspective from the end product property out. And this is already done in other areas as well. And then you're looking, how can I reach these end product properties? Is there a possibility to use other materials? Is it possible to use other processing step or innovation or technological platforms? And this is only an perspective how you are looking at the food production. Not sticky to end product properties. And then, especially you are looking to Germany, and you want to have an acceptance, especially Germany is very conservative in when foods are concerned, yes. Then everybody wants to have the same raw material. You can make this type of food only with these raw materials, with these steps. And you're not open, or they are not open, we are all not open in Germany, to change something at the raw material side and the processing side. Because you look not at the end product properties. Here, we want to go a totally another way. We say, okay, I want to have a crispiness inside. And this is what we already did. We made some shrimps out of starch-based raw materials. And we are very far with it to really have this fibrillar structure already, or a structure with a totally different raw material. And this is only a perspective how you are looking at the end product, sticking to end product qualities, parameters, and be open in all what is done before, or what you are using in before.
Okay, thanks.
I hope I could answer.
Thanks very much, Prof. Becker. If there are no more questions, I'd like to move on to the final presentation for the day. I'd like to invite our final speakers, Prof. Daniela Roos